We're going way back to the beginning of the year, talking imaginary numbers and radicals. Imaginary numbers come from square roots of negative numbers. So the square root of -1 is actually known as I, or imaginary. And then we start running into the powers of I when they start multiplying together. So if I do I squared, or the square root of -1 squared, the square and the square root just cancel out and give us -1. Moving on, I to the third is going to be I squared times I, or -1 times I, which is -I. I to the fourth is going to be +1. Now remember, you don't have to memorize these. You can type these into your calculator using the second decimal point, and that'll give you the first few powers of I. Now the problem you're going to run into is, on the Regents or my final, we're going to do higher powers than 4. So if I wanted to do I to the 65th times I to the 26th, I could either simplify each of those accordingly, or I actually find it easier to use one of our laws of exponents here. When I'm multiplying things with the same base, I can add the exponents. So 65 and 26 makes 91. So now I'm just trying to figure out, where does I to the 91 fall in this cycle of 4 that keeps happening over and over and over again? So I can do that one of two ways. Well, one of three ways. I could count till I get to the 91st one. That'll take me a while. Or I could think of multiples of 4 that are close to 91. Well, 4 times 22 is 88, so that means this is I to the 88th. And then when I go back up to the top, this will be 89, 90, and 91. So I to the 91st is the same as I to the third, which is actually equal to -I. Or my other option is to long divide 91, that exponent. Let's find out how many full cycles of 4 we're going to go through. We're going to go through 22 full cycles with 3 left over. So I to the third is going to be my answer, which also gives me -1. You've got your choice of which way you want to figure those out. Next up, operations with radicals. When you're adding or subtracting radicals, they have to have the same last name in order to combine or to get married. And then they keep that same last name. If you're multiplying or dividing, you simply multiply the coefficients or divide the coefficients, and same thing with the radicals. So this problem here, these two radicals want to be subtracted, so we are going to need to get them to have the same last name by attacking with some of the perfects. Now my first job here is going to be to pound out these negatives and turn them into imaginary numbers. Now the perfects are going to come along. A perfect square, the biggest perfect square that's going to attack 72 is 36, and 36 goes into 72 twice. So the square root of 36 is really 6, so this will become 6i radical 2. My other person here in the back, radical 32, can be attacked by radical 16, and it goes into 32 twice. The square root of 16 is 4. 5i times 4 will be 20i, radical 2. And notice those same last names there. So now we're going to subtract 6i, take away 20i, is -14 imaginary, and the last name stays the same. Simplifying radicals with variables, I'm actually going to use another law of our exponents that says when you're doing the nth root of x to the m, that's the same thing as x to the m over n power. So this example that I provided here, I could rewrite this as 24 x to the 6th, y to the 10th, z to the 5th, all to the 1/3 power, because cube rooting is the same thing as a 1/3 exponent. And then I can use another law of our exponents to kind of distribute this 1/3 into all these pieces. So 24 to the 1/3 power, if you do that on your calculator, you're going to get a decimal. So let's try using perfect cubes to simplify the 24. Well, perfect cubes, 1 times 1 times 1 is 1. 3 times 3 times 3 is 27. 2 times 2 times 2 makes 8. 4 times 4 times 4 makes 64. So which one of those will go into 24 evenly? Well, the 8 will. 8 goes into 24 3 times. So the cube root of 24, I'm going to break up into the cube root of 8 and the cube root of 3. And the cube root of 8 is 2. And then I still have my cube root of 3 here. Then for my variables in the exponents, when I have an exponent to an exponent, we multiply the exponents. So 6 times 1/3 for the x's is going to be 2, 1/3 of 6. For my y's, 10 times 1/3 is 3 and 1/3. So my 1/3 is going to be that radical. And then 5 times 1/3 is 1 and 2/3. And then I'm just going to regroup this all together in a nice orderly fashion. I've got a 2 x squared y cubed z to the first. And then my cube root parts, I've got a 3, a y to the first, and a z to the second. All these problems we've done so far have been expressions. Now we're going to shift gears into an equation where we're actually solving for x. What value or values of x will make this equation be true? So I've got to get rid of that radical. So the opposite of square rooting something is squaring it. So I'm going to square the left side. That will cancel out the square root. But whatever I do on the left, I have to do on the right. So I'm going to square the right side, which means I'm going to have to multiply this by itself 2 times. So we're going to have to do the double distributing. X times x is x squared, minus 3x minus another 3x makes minus 6x plus 9. Now I've turned this equation into a quadratic equation. So let's make this equal to 0 by minusing 30 and adding 2x. That'll give me my 0 is equal to x squared minus 4x minus 21. Now from here I could do the quadratic formula or completing the square, or I'm actually just going to factor this because I know numbers that times to 21 and add or subtract to 4 are 7 and 3. The bigger number gets that middle sign, so this will be minus 7 plus 3. And Mr. Squiggly comes along and says our two possible answers are positive 7, negative 3. And when you plug both of those back into the original equation to check the 7 works, you'll get a 4 on both sides of the equal sign. However, the negative 3 does not check out. That's an extraneous answer that gets rejected. So x equals 7 is the only answer.